Please subscribe to support the channel. In the vast expanse of the cosmos, hidden within the depths of a distant galaxy cluster, lies an object so massive and so profoundly powerful that it challenges our very understanding of how the universe constructs its most extreme phenomena. This object is the supermassive black hole at the center of the galaxy Holm 15A, situated approximately 700 million light-years from Earth in a region of space known as the Abell 85 galaxy cluster. To grasp the sheer enormity of this cosmic giant, consider that its mass has been calculated at roughly 40 billion times that of our Sun. To put this in perspective, if you were to take every planet, asteroid, comet, and particle of dust in our entire solar system and multiply that mass by tens of thousands, you would still fall dramatically short of comprehending the scale of this single object. It represents not merely a black hole of impressive dimensions, but rather a monument to the extreme processes that have shaped the universe over billions of years of cosmic evolution. When we speak of Holm 15A, we must distinguish it from the more familiar black holes that populate scientific discussions and capture public imagination. The universe contains black holes of many varieties, but they generally fall into distinct categories based on their formation mechanisms and resulting masses. Stellar mass black holes, which form when massive stars exhaust their nuclear fuel and collapse catastrophically inward, typically range from about 3 to several dozen times the mass of the Sun. These objects, while certainly extreme by terrestrial standards, represent the smaller end of the black hole spectrum. Then we encounter the intermediate mass black holes, a somewhat mysterious category that bridges the gap between stellar mass and supermass varieties, with masses ranging from hundreds to thousands of solar masses. The formation mechanisms for these intermediate objects remain subjects of active research and debate among astrophysicists. But it is the supermassive black holes that truly command our attention when contemplating the universe's most extreme environments. These behemoths, residing at the centers of most large galaxies, typically possess masses ranging from millions to billions of times that of the Sun. Our own Milky Way galaxy harbors such an object, known as Sagittarius A, with a mass of approximately 4 million solar masses. While this might sound enormous, and indeed it is by any reasonable standard, it pales in comparison to the true giants of the cosmos. Holm 15A exists in a category that some researchers have begun calling ultramassive black holes, objects so extraordinarily large that they occupy the extreme tail of the mass distribution for these cosmic entities. What makes these objects particularly fascinating is not merely their size, but what their existence implies about the history of structure formation in the universe. Every supermassive black hole has a story to tell about the galaxy that hosts it, about the countless merger events and accretion episodes that have occurred over billions of years of cosmic evolution. But ultramassive black holes like the one in Holm 15A speak to particularly dramatic and complex histories, suggesting multiple major merger events and sustained periods of rapid growth that push these objects far beyond the typical size range for galactic central black holes. The relationship between a galaxy and its central black hole represents one of the most intriguing connections in astrophysics, with the black hole's growth intimately tied to the galaxy's own evolution through cosmic time. The journey to discovering and characterizing the black hole at the heart of Holm 15A represents a triumph of modern observational astronomy and theoretical physics. The galaxy itself had been cataloged and observed for many years as part of studies of the Abell 85 galaxy cluster. But the true nature of its central black hole remained elusive until relatively recently. In 2019 and 2020, teams of astronomers working at the Max Planck Institute for Extraterrestrial Physics in Germany, along with collaborators at other institutions around the world, published groundbreaking research that revealed the extraordinary mass of this object. Their work relied on sophisticated observations gathered from multiple telescopes, combining data across different wavelengths of light to build a comprehensive picture of the galaxy's central regions. The researchers employed advanced spectroscopic techniques, analyzing the light coming from stars orbiting deep within the galaxy's core region. By studying how this light was shifted toward redder or bluer wavelengths due to the Doppler effect as stars move toward or away from us in their orbits, the astronomers could reconstruct the gravitational field in which these stars moved. This painstaking work required not only exceptional observational data, but also complex mathematical modeling to account for the three-dimensional motions of stars in a galaxy seen from a single vantage point hundreds of millions of light years away. The announcement of their findings sent ripples through the astronomical community, While astronomers had suspected that home galaxy A had a very massive black hole based on the properties of a toast galaxy, the actual measured mass exceeded many expectations. At approximately 40 billion solar masses, with some uncertainty in this measurement that we will explore further, the black hole ranked among the most massive ever discovered. The precision required to make such measurements across such vast cosmic distances cannot be overstated. Every photon of light that reached the telescopes using this study had traveled for roughly 700 million years, departing the vicinity of Holm 15A when life on Earth was just beginning to experiment with multicellular forms. During that immense journey through expanding space, these photons maintained encoded within their properties information about the extreme gravitational environment they had escaped. The astronomer's task was to extract that information, to read the story written in starlight about an object whose gravitational grip is so powerful that nothing, not even light itself, can escape once it crosses the point of no return we call the event horizon.
To truly appreciate what makes Holm 15A so remarkable, we must understand the galaxy that serves as its cosmic home. Holm 15A is not just any galaxy, but rather what astronomers classify as a brightest cluster galaxy, or BCG in astronomical shorthand. These galaxies occupy special positions in the cosmic hierarchy of structure. Galaxy clusters represent some of the largest gravitationally bound structures in the universe, containing hundreds or even thousands of individual galaxies, all held together by their mutual gravitational attraction, along with the gravitational influence of vast amounts of dark matter that pervades and surrounds the cluster. At the center of many such clusters sits a single dominant galaxy that outshines all others in the cluster, often having grown to its current size by cannibalizing smaller galaxies that wandered too close over billions of years. These brightest cluster galaxies typically exhibit distinctive properties that set them apart from other large galaxies. They tend to have extended envelopes of stars spreading far beyond their cores, diffuse outer regions that bear witness to past merger events, and they host some of the most massive black holes known to exist. The Abell 85 galaxy cluster itself provides crucial context for understanding Holm 15A. This cluster contains hundreds of galaxies spread across millions of light-years of space, all engaged in a complex gravitational dance that has played out over billions of years. The cluster's total mass, including both visible matter and dark matter, reaches into the hundreds of trillions of solar masses, making it one of the more massive galaxy clusters in our cosmic neighborhood. The history of Abell 85 has been shaped by numerous subclusters merging together over time, with smaller groups of galaxies falling into the cluster's gravitational well and being incorporated into the larger structure. Holm 15A sits at the dynamical center of this vast assemblage, the deepest point in the cluster's gravitational potential well. This central position means that over cosmic time, Holm 15A has had the first opportunity to capture and merge with infalling galaxies and has experienced more merger events than typical cluster galaxies. Each time another galaxy falls toward the cluster center and merges with Holm 15A, the collision brings not only additional stars and gas, but also the companion galaxy's own central supermassive black hole, setting the stage for an eventual black hole merger that adds to the growing mass of Holm 15A's central black hole. The methods scientists employed to determine the mass of this ultramassive black hole showcase the impressive capabilities of modern astrophysics to probe the universe's most extreme environments. The fundamental challenge in measuring a black hole's mass, particularly one residing at the center of a galaxy hundreds of millions of light-years away, lies in the fact that the black hole itself emits no light. We cannot see it directly, cannot photograph it in the way we might image a star or galaxy. Instead, astronomers must infer the black hole's presence and properties by observing its gravitational effects on surrounding matter. For supermassive black holes at galaxy centers, the primary technique involves what's called stellar kinematics, the study of how stars move under the gravitational influence of the central mass concentration. The basic principle is straightforward enough. More massive objects exert stronger gravitational pulls, causing nearby objects to orbit faster. By measuring the velocities of stars at various distances from a galaxy's center, astronomers can reconstruct the mass distribution in the galaxy's core and determine how much mass must be concentrated in the central black hole to produce the observed stellar motions. However, the practical implementation of this technique involves layers of complexity. First, astronomers must obtain high-quality spectra of the galaxy's central regions, spreading the light out into its component wavelengths to measure the Doppler shifts that reveal stellar velocities. For a galaxy as distant as Holm 15A, this requires large telescopes with sensitive spectrographs and long observation times to gather sufficient light. The light from any particular star in Holm 15A is far too faint to detect individually at such distances. Instead, astronomers measure the integrated light from thousands or millions of stars simultaneously, analyzing the combined spectrum to extract information about the distribution of stellar velocities at each position in the galaxy. The analysis becomes even more sophisticated when astronomers create maps showing how stellar velocities vary with position across the galaxy's face, building up a two-dimensional picture of the gravitational field. Converting these velocity measurements into a black hole mass estimate requires careful modeling that accounts for numerous factors. The stars we observe in a galaxy's central regions are not all orbiting at the same distance from the black hole, and they're not all moving in the same plane. Instead, we see a complex, three-dimensional distribution of stellar orbits projected onto the two-dimensional sky. Astronomers must use sophisticated mathematical techniques to deproject these observations, essentially working backward from the two-dimensional data to infer the three-dimensional distribution of stellar orbits. This process involves making assumptions about the orbital structure of stars in the galaxy, assumptions that can be tested and refined by comparing model predictions to observations. Additionally, the gravitational field near the galaxy's center depends not only on the black hole's mass, but also on the distribution of stars and dark matter in the region. Astronomers must account for these additional mass components to isolate the black hole's specific contribution to the gravitational field. For Holm 15A, this modeling revealed that to explain the high stellar velocities observed in the galaxy's core, a central mass concentration of approximately 40 billion solar masses was required, far exceeding what could be explained by stars alone. One of the most striking and scientifically significant features of Holm 15A is the unusual structure of its galactic core. When astronomers analyzed high-resolution images of the galaxy, they discovered something unexpected: a significant depletion of stars in the central region, creating what astronomers call a core or stellar deficit. While many large elliptical galaxies show some degree of core structure, with stellar density that stops rising or even decreases in the very center, the core in Holm 15A is extraordinarily large and pronounced. Extending outward for several thousand light-years from the galaxy's center, this region contains far fewer stars than would be expected based on the galaxy's overall light profile. Quantitatively, estimates suggest that the equivalent of several billion solar masses worth of stars are missing from the central region compared to what would be expected in a galaxy without such a core. This is not merely an academic curiosity, but rather a crucial clue to understanding the black hole's history and growth. The existence of such large stellar cores and massive elliptical galaxies has been recognized for decades, but explaining their formation has challenged theorists. Several mechanisms might contribute to core formation, but for a core as large as the one observed in Holm 15A, the most compelling explanation involves the dynamics of binary supermassive black holes. When two galaxies merge, they each bring their own central supermassive black hole to the collision. Initially separated by tens of hundreds of thousands of light-years apart, these black holes gradually spiral inward as dynamical friction with the surrounding stars and gas cause them to lose energy and angular momentum. Eventually, the two black holes form a gravitationally bound pair, a binary system orbiting their common center of mass. As this binary system continues to evolve, it interacts with stars that pass nearby, essentially playing a game of gravitational pinball. In these interactions, the binary typically ejects stars at high velocities, flinging them outward from the galaxy's core. This process efficiently removes stars from the central region, gradually excavating the observed core. The larger and more massive the black hole binary, the larger the core it can create and the more stars it can eject. The extreme core size in Holm 15A suggests that the galaxy likely experienced not just one major merger event, but multiple mergers involving very massive black holes, each merger episode contributing to the excavation of the central stellar deficit.
The story of how Holm 15A's central black hole grew to its current enormous mass is fundamentally a story about cosmic violence played out over billions of years. No black hole begins its existence with a mass of 40 billion suns. Instead, such ultramassive objects must grow over time through two primary mechanisms: accretion of matter and merger with other black holes. In the early universe, the first black holes likely formed from the collapse of massive stars, or possibly through more exotic mechanisms that created intermediate mass seed black holes in the first generations of galaxies. These seed black holes, while already massive by stellar standards, would have had masses perhaps thousands or at most millions of times that of the Sun. From these seeds, supermassive black holes grew by feeding on gas and stars in their host galaxies, gradually accumulating mass through a process called accretion. When material falls toward a black hole, it typically doesn't plunge straight in, but instead forms a swirling accretion disk, with matter gradually spiraling inward as friction and magnetic forces transport angular momentum outward. As material in the accretion disk gets compressed and heated by the intense tidal forces near the black hole, it reaches temperatures of millions of degrees, hot enough to radiate enormous amounts of energy across the electromagnetic spectrum. This is how quasars and active galactic nuclei generate their tremendous luminosity, powered not by nuclear fusion like stars, but by the gravitational potential energy of matter falling into a black hole. However, while accretion can certainly grow black holes to impressive sizes, reaching masses of billions of solar masses through accretion alone faces significant challenges. One fundamental issue is that as a black hole accretes matter and radiates energy, the radiation pressure from this intense emission can actually push away infalling material, creating a self-regulating feedback loop that limits how fast the black hole can grow. This limitation is encoded in what's called the Eddington limit, which describes the maximum luminosity a steadily accreting object can achieve before radiation pressure balances gravitational attraction. For a black hole accreting at the Eddington limit, there's a corresponding maximum growth rate, often called Eddington-limited accretion. Even under optimal conditions, with sustained Eddington-limited accretion, growing a black hole from a stellar mass seed to billions of solar masses requires hundreds of millions to billions of years. For an ultramassive black hole like Holm 15A, accretion alone seems insufficient to explain its extraordinary mass, particularly given that the universe has only existed for about 13.8 billion years. This is where black hole mergers become crucial to this story. When two galaxies collide and eventually merge, a process that can take hundreds of millions of years to fully complete, their central black holes are destined to come together. Initially, as the galaxies interpenetrate and their stellar populations begin mixing, the two black holes remained embedded in their respective galactic cores, separated by vast distances. Dynamical friction gradually brings them closer together over tens or hundreds of millions of years. This friction isn't literally friction in the everyday sense, but rather a gravitational drag effect where the black hole's motion through the galaxy's stellar and dark matter distribution causes them to slow down and sink toward the merged galaxy's center. Once the black holes get close enough to form a gravitationally bound binary, they continue spiraling inward through interactions with individual stars that pass near the binary orbit. Finally, when the separation shrinks to a fraction of a light year or less, The black holes enter a regime where emission of gravitational waves becomes the dominant mechanism, removing energy and angular momentum from the system. These ripples in space-time itself, predicted by Einstein's general relativity and directly detected for the first time in 2015, carry away energy and cause the black holes to spiral together ever faster until they ultimately merge in a violent collision that creates a single, more massive black hole. For Holm 15A, sitting at the center of a major galaxy cluster and having experienced numerous galaxy merger events over its lifetime, black hole mergers have almost certainly played the dominant role in assembling its current extraordinary mass. Each time Holm 15A merged with another galaxy, particularly another massive galaxy containing its own multi-billion solar mass black hole, the collision added substantially to the central black hole's mass. Theoretical models of galaxy cluster assembly and brightest cluster galaxy growth suggest that galaxies like Holm 15A might have experienced dozens of significant merger events over cosmic time, with several being major mergers involving comparably massive galaxies. If we imagine a history where Holm 15A underwent, say, 5 to 10 major mergers with galaxies each containing black holes of several billion solar masses, along with numerous smaller merger events and sustained periods of gas accretion, we can begin to construct a plausible pathway to the current 40 billion solar mass. Each merger event wouldn't simply add the masses of the two progenitor black holes. It would also provide fresh gas fuel from the merger-induced disturbances, potentially triggering episodes of enhanced accretion. The resulting picture is one of sustained growth over billions of years, with the black hole's mass curve climbing steeply during major merger events and more gradually during quiescent periods between mergers. An intriguing consequence of supermassive black hole mergers involves the gravitational waves emitted during these cosmic collisions. When two black holes merge, they don't emit gravitational waves symmetrically in all directions. Instead, the gravitational wave emission can have a preferred direction, carrying away not only energy and angular momentum, but also linear momentum. This asymmetric emission creates what physicists call a gravitational wave recoil or kick, where the merged black hole receives a velocity impulse that can be substantial. Depending on the masses, spins, and orbital parameters of the merging black holes, recoil velocities can range from relatively modest values of tens or hundreds of kilometers per second up to potentially several thousand kilometers per second for particularly asymmetric configurations. For context, the escape velocity from a massive galaxy like Holm 15A is typically around 1,000 kilometers per second, meaning that a sufficiently strong gravitational wave kick could actually eject the merged black hole from its host galaxy entirely, sending it wandering through intergalactic space. Even kicks smaller than the escape velocity can displace the black hole from the galaxy's center, causing it to oscillate back and forth through the core region for millions of years before settling back to the center. The connection between gravitational wave recoil and the large stellar core observed in Holm 15A represents an active area of research and debate. Some theoretical models suggest that a displaced black hole, oscillating through the galaxy's core after receiving a recoil kick, could interact with stars throughout a large volume and contribute to excavating an extended stellar deficit. Alternatively, or additionally, the multiple binary black hole phases that occurred during the galaxy's merger history before the component black holes finally coalesced would have efficiently ejected stars from the central region through gravitational slingshot interactions. The pronounced core in Holm 15A likely reflects a combination of these effects accumulated over multiple merger events. Each major merger would have brought together two supermassive black holes, created a binary that ejected stars while spiraling together, and then concluded with a merger that possibly imparted a recoil kick to the remnant black hole. Repeat this process several times over billions of years, and the cumulative effect on the stellar distribution in the galaxy's core could be dramatic. The fact that Holm 15A has retained such a massive black hole despite multiple merger events suggests that any gravitational wave kicks it experienced
were not strong enough to eject it from the galaxy, but they may well have been strong enough to contribute to the core excavation process.
When discussing ultramassive black holes, comparisons inevitably arise with other candidates for the title of most massive black hole in the universe. The competition is, shall we say, quite literally astronomical. One prominent contender is the black hole at the center of the quasar TON 618, with mass estimates reaching as high as 66 billion solar masses. Though these measurements come with substantial uncertainties, TON 618 sits at a much greater distance than Holm 15A, approximately 10 billion light-years away, meaning we observe it as it existed when the universe was only about a quarter of its current age. The black hole's mass in TON 618 is estimated using different techniques than those applied to Holm 15A, primarily based on the properties of the quasar's broad emission lines and its luminosity, methods that involve their own sets of assumptions and uncertainties. Another ultramassive candidate is Phoenix A, the central black hole in the Phoenix cluster located about 5.7 billion light-years away, with mass estimates also in the range of tens of billions of solar masses. IC 1101, one of the largest known galaxies by physical extent, is sometimes mentioned as potentially hosting an ultramassive black hole, though actual mass measurements remain uncertain and contested. What makes comparing these objects challenging is not just the different measurement techniques employed, but also the fundamental uncertainties inherent in each method. For relatively nearby galaxies like Holm 15A, where we can at least in principle resolve individual stars or stellar populations in the galactic core and measure their velocities, the stellar kinematics technique provides relatively direct constraints on the central mass. But even here, uncertainties arise from assumptions about the stellar orbital structure, the contribution of dark matter to the mass budget, and observational limitations in measuring faint stellar populations. For more distant quasars like TON 618, where we cannot resolve the host galaxy structure at all, astronomers must rely on indirect methods. One common approach uses the relationship between a quasar's luminosity and the estimated mass of its accretion disk, combined with empirical relationships between black hole mass and certain observational properties of the quasar spectrum. These methods have been calibrated using better studied nearby active galactic nuclei, but extrapolating them to the most extreme objects introduces additional uncertainties. The upshot is that while we can say with reasonable confidence that Holm 15A contains one of the most massive black holes ever measured, and that TON 618 and a few other candidates may be comparable or possibly more massive, the uncertainties in all these measurements mean we cannot definitively crown a single champion. What we can say is that these objects collectively define the extreme end of the black hole mass spectrum, and that studying them provides unique insights into black hole and galaxy evolution. The relationship between the mass of a galaxy's central supermassive black hole and the properties of the galaxy itself represents one of the most important and somewhat puzzling discoveries in modern astrophysics. Beginning in the late 1990s and early 2000s, astronomers found clear correlations between black hole mass and several properties of the host galaxy's bulge, the central concentration of stars in disk galaxies, or the entire stellar body in elliptical galaxies. The tightest correlation, known as the M-sigma relation, connects black hole mass to the velocity dispersion of stars in the galaxy's bulge. Velocity dispersion, denoted by the Greek letter sigma, measures the typical random velocities of stars, basically how fast they're moving in random directions, as opposed to any organized rotational motion. What astronomers discovered is that more massive bulges, with higher stellar velocity dispersions, systematically contain more massive central black holes, with the relationship following a relatively tight power law. Specifically, black hole mass scales roughly as a velocity dispersion raised to a power between 4 and 5, meaning a galaxy with twice the velocity dispersion tends to have a black hole about 16 to 32 times more massive. This correlation extends over several orders of magnitude in black hole mass, from millions to billions of solar masses, and the scatter around the relation is remarkably small, suggesting a fundamental connection between black hole growth and galaxy formation. The physical origin of the M-sigma relation remains an active area of theoretical research, but most explanations invoke feedback processes that regulate both star formation and black hole growth in a coordinated way. When a supermassive black hole accretes matter, particularly during phases of rapid accretion that power quasar activity, it doesn't simply grow quietly. Instead, the accretion process releases tremendous amounts of energy through radiation, high-velocity winds, and powerful jets of matter ejected at nearly the speed of light. This energy couples to the surrounding gas in the galaxy,
heating it, compressing it, and in some cases driving galactic-scale outflows that expel gas from the galaxy entirely. This active galactic nucleus feedback can both trigger bursts of star formation through compression of gas clouds and, if strong enough, eventually shut down star formation by removing or heating the cold gas needed to form new stars. The result is a self-regulating system where black hole growth and stellar population growth influence each other. Galaxies that undergo more vigorous star formation and assemble larger stellar bulges also provide more fuel for their central black holes to grow, while the black holes regulate the star formation through feedback, ultimately establishing the observed correlation. The question of where Holm 15a fits into this picture is intriguing and somewhat complex. Given the black hole's mass of about 40 billion solar masses, the m-sigma relation would predict that the galaxy should have an extraordinarily high stellar velocity dispersion, corresponding to a very massive stellar bulge. Indeed, Holm 15a is an extremely massive galaxy, with a total stellar mass estimated at several trillion solar masses, far more massive than our Milky Way. The stellar velocity dispersion in the galaxy is correspondingly high, several hundred kilometers per second, reflecting the deep gravitational potential well of this massive system. However, some analyses have suggested that Holm 15a's black hole might be somewhat overmassive compared to what the m-sigma relation would predict, lying above the main correlation established by less extreme systems. If true, this could indicate that the processes that build such ultramassive black holes in brightest cluster galaxies involve additional physics not captured in the standard m-sigma relation. For example, black hole mergers might be more efficient at building a black hole mass compared to stellar mass in these extreme systems, or the multiple merger events these galaxies experience could preferentially grow the black hole relative to the stellar population. Alternatively, the apparent offset might be an artifact of measurement uncertainties or reflect the unusual stellar distribution with the large core, which could affect how we measure and interpret the velocity dispersion. Resolving this question requires both better observational data and more sophisticated theoretical models of how the most massive galaxies and their black holes co-evolve.
To truly appreciate the extremity of Holm 15a's central black hole, it helps to consider what its event horizon would look like. The event horizon represents the boundary of no return around a black hole, the surface beyond which the escape velocity exceeds the speed of light, making escape impossible even for light itself. For a non-rotating black hole, the event horizon radius is given by the Schwarzschild radius, calculated using the simple formula derived from general relativity. For Holm 15a's black hole, with its mass of approximately 40 billion solar masses, the Schwarzschild radius works out to roughly 118 billion kilometers. To put this almost incomprehensible distance into more familiar astronomical terms, it equals about 790 astronomical units, where 1 astronomical unit is the average distance from Earth to the Sun, approximately 150 million kilometers. The orbits of all the planets in our solar system, from Mercury to Neptune, fit comfortably within a radius of about 30 astronomical units. Pluto's orbit extends out to roughly 40 astronomical units at its average distance. The event horizon of Holm 15a's black hole would extend nearly 20 times farther than Pluto's orbit. If we could somehow place this black hole at the center of our solar system, its event horizon would swallow not just all the planets, but would reach far out into the Kuiper belt, the region of icy bodies beyond Neptune's orbit. In fact, it would extend nearly halfway to the inner edge of the Oort cloud, the hypothesized spherical shell of comets that marks the outermost boundary of the Sun's gravitational dominance. This enormous size has profound implications for what the black hole's environment would be like. One counterintuitive feature of very massive black holes is that the tidal forces at their event horizons are actually relatively mild, far less extreme than those at the event horizon of a stellar mass black hole. Tidal forces arise from the difference in gravitational pull across a finite-sized object. The fact that one side of an object experiences stronger gravity than the other side when in a gravitational field. For a stellar mass black hole with an event horizon radius of just a few kilometers, the tidal forces at the horizon are enormous, capable of ripping apart any ordinary matter that approaches.
The dramatic spaghettification effect, where objects are stretched into long, thin strands by tidal forces, would occur well before reaching the event horizon of such compact objects. But for an ultramassive black hole, like the one in Holm 15a, the event horizon is so far from the black hole's center that the gravitational gradient across even a large object like a spaceship or a person is relatively small at the horizon itself. In principle, an astronaut could cross the event horizon of such a black hole without immediately experiencing destructive tidal forces. Of course, this is only a momentary reprieve, as tidal forces would still grow dramatically as one fell toward the singularity at the center. And of course, crossing the event horizon means there's no possibility of escape or communication with the outside universe. But the initial crossing would be almost gentle, in eerie contrast to the violent disruption that would occur at the event horizon of smaller black holes. The gravitational influence of Holm 15a's black hole extends far beyond its event horizon through what astronomers call the sphere of influence. This concept describes the region around a black hole where the black hole's gravitational effect on stellar orbits dominates over the collective gravitational pull of all the other stars in the galaxy. The radius of the sphere of influence depends on both the black hole's mass and the stellar mass density and velocity dispersion in the surrounding galaxy. For Holm 15a, with its exceptionally massive black hole, the sphere of influence extends outward for several thousand light-years from the galactic center. Within this region, stellar orbits are primarily determined by the black hole's gravity. Stars on orbits that pass close to the black hole can achieve tremendous velocities, potentially reaching significant fractions of the speed of light in the innermost regions, though we cannot observe individual stars at such distances. Even at the outer edge of the sphere of influence, thousands of light-years from the black hole, its gravitational effect still measurably influences stellar dynamics. Outside the sphere of influence, the cumulative gravity of all the stars in the galaxy dominates, and the black hole's presence becomes just one component of the overall gravitational potential, important but not controlling. The large sphere of influence around ultramassive black holes like this one is crucial for astronomers attempting to measure the black hole's mass, as it means there's a larger region where the black hole's gravitational signature appears in stellar kinematics data. Thinking about matter falling into such a black hole raises fascinating questions about the experience of crossing the event horizon and falling toward the singularity. According to general relativity, from the perspective of an external observer watching an object fall toward a black hole, the object would appear to slow down as it approaches the event horizon, with the light from it becoming increasingly redshifted and dimmed. The object would appear to freeze at the horizon, asymptotically approaching but never quite crossing from the external observer's point of view. This occurs because of the extreme time dilation near the event horizon. Time as measured by the falling object flows at a different rate than time measured by a distant observer. However, from the perspective of the infalling observer itself, nothing particularly special happens at the moment of crossing the event horizon. For an ultramassive black hole, as we've discussed, the tidal forces at the horizon are manageable, and the local curvature of space-time, while certainly extreme compared to everyday experience, is less sharply curved than for smaller black holes. The infalling observer would cross the event horizon in a finite time by their own clock, and continue falling inward toward the singularity at the center. Once inside the horizon, the roles of space and time become interchanged in a sense. The singularity is not a place in space that you can choose to go to. Rather, it lies in your unavoidable future, as certain as next Tuesday. All world lines inside the event horizon lead inexorably to the singularity. What happens at the singularity remains one of the great unsolved problems in theoretical physics. Classical general relativity predicts that all infalling matter collapses to infinite density at a geometric point or ring, a mathematical singularity where the equations of general relativity break down and cease to provide meaningful predictions. Most physicists believe this signals not the actual existence of infinite densities, but rather the limitation of general relativity as a complete description of nature. A quantum theory of gravity, which would merge general relativity with quantum mechanics, would presumably replace the singularity with some more physically reasonable structure.
Several candidate theories, including string theory and loop quantum gravity, predict modifications to the structure of spacetime at extremely small scales that might resolve the singularity. But without experimental guidance, and without a complete quantum theory of gravity, we can only speculate. What we can say is that any matter or energy falling into the black hole adds to its mass, and thus to the size of its event horizon, with the added mass energy becoming part of the black hole's total gravitational field as characterized by just a few parameters: mass, angular momentum, and electric charge in the classical description. The role of dark matter in understanding systems like Holm 15A and the Abell 85 cluster cannot be overstated. Dark matter, the mysterious form of matter that interacts primarily through gravity while remaining invisible to electromagnetic radiation, dominates the mass budget of galaxy clusters. While the luminous matter we can see, consisting of stars and hot X-ray emitting gas, contributes substantially to a cluster's total mass, observations of cluster dynamics and gravitational lensing reveal that dark matter outweighs luminous matter by factors of 5 to 10 or more. In Abell 85, the dark matter forms an extended halo pervading the cluster, providing the gravitational scaffolding that holds the cluster together and determines the motions of galaxies within it. Holm 15A, sitting at the cluster center, is embedded within the densest region of this dark matter distribution. When astronomers model the galaxy structure to infer the central black hole's mass from stellar kinematics, they must account for the dark matter halo's contribution to the gravitational potential. Dark matter within the galaxy itself, as well as in the immediate cluster environment, affects the interpretation of stellar velocities and the resulting black hole mass estimate.
Moreover, dark matter plays a crucial role in the formation and assembly history of systems like Holm 15A. In the current cosmological paradigm, structure in the universe forms hierarchically, with small dark matter halos forming first and then merging over time to build progressively larger structures. Galaxies form within dark matter halos, with the baryonic matter of gas and stars falling into the gravitational potential wells defined by the dark matter. Galaxy clusters represent the largest viralized structures in this hierarchy, having assembled from the merger of many smaller groups and individual galaxies. Brightest cluster galaxies, like Holm 15A, grow primarily through this hierarchical assembly process, capturing smaller galaxies as they fall toward the cluster center and merging with other massive galaxies during major cluster merger events. The dark matter dynamics drive this assembly process, with dark matter halos merging first and dragging their embedded galaxies along. The multiple merger events that build Holm 15A's extraordinary central black hole were enabled by the underlying dark matter structures bringing galaxies together. In this sense, understanding the black hole's growth requires understanding the dark matter scaffolding on which visible structures are built. The feeding mechanisms that allowed Holm 15A's black hole to accumulate such enormous mass over cosmic time involve both the direct accretion of gas and the consumption of entire stars that ventured too close. In the early universe, when galaxies were richer in gas and merger events were more frequent, supermassive black holes likely experienced sustained periods of rapid accretion. During these active phases, gas funneled toward the galactic center through various mechanisms would form accretion disks around the black hole, with matter gradually spiraling inward and eventually crossing the event horizon. The rate of accretion can vary enormously depending on the availability of cold gas in the galaxy's central regions and the efficiency with which that gas can lose angular momentum and fall inward. During major galaxy mergers, the collision disrupts both galaxy structures, driving gas toward the center through gravitational torques and shocking the gas, which can trigger vigorous bursts of both star formation and black hole accretion. These merger-driven accretion episodes might represent periods of particularly rapid black hole growth, when the black hole could potentially accrete at or near the Eddington limit for millions of years at a time. Beyond gas accretion, black holes can also grow by directly capturing stars that pass too close. When a star on an unlucky orbit approaches within a certain critical distance of a black hole, the tidal forces become strong enough to overcome the star's self-gravity and tear it apart in what astronomers call a tidal disruption event. For stellar mass black holes, this tidal disruption radius lies inside the event horizon, meaning stars simply fall in whole. But for supermassive and ultramassive black holes, the tidal disruption radius extends well outside the event horizon.
When disruption occurs, roughly half of the star's mass typically remains bound to the black hole and falls back over weeks to months, creating a bright flare of emission as this material accretes. The other half gains enough energy to escape. For a black hole as massive as the one in Holm 15A, tidal disruptions would occur relatively far from the event horizon, several hundred to thousands of Schwarzschild radii, regions where general relativistic effects are strong, but not as extreme as near the horizon itself. Over billions of years, the cumulative mass gained from tidal disruption events, along with the occasional direct capture of whole stars that approach within the event horizon on plunging orbits, adds to the black hole's growth, though this mechanism likely contributes less total mass than gas accretion and black hole mergers. The stellar density in the immediate vicinity of an ultramassive black hole like this one presents an interesting environment for stellar dynamics. Close to the black hole, within the inner regions of its sphere of influence, stars orbit with very short periods and high velocities. The orbital periods for stars just outside the event horizon would be measured in hours or days, with velocities approaching the speed of light. Slightly farther out, at distances of tens or hundreds of short-lived radii, orbital periods might be months to years, still dramatically shorter than typical stellar orbital periods in galactic disks. These stars experience the extreme gravitational field of the black hole, with significant relativistic effects influencing their orbits. General relativistic orbital precession, where the elliptical orbit itself slowly rotates, becomes substantial. Light from stars in these regions would be gravitationally redshifted and subject to gravitational lensing effects. Of course, we cannot observe individual stars in these regions of Holm 15A given its enormous distance, but we know such populations must exist based on our understanding of stellar dynamics and our observations of similar environments around closer supermassive black holes. The stars that do populate these regions represent a transient population in a sense. Many will eventually be perturbed onto plunging orbits and consumed by the black hole, while others might gain energy from gravitational interactions and be ejected to larger radii or even escape the galaxy entirely. One of the profound questions that objects like Holm 15A raise concerns whether there exists an upper limit to how massive a black hole can grow. From a theoretical perspective, several factors might constrain maximum black hole masses. One consideration involves the feedback processes we discussed earlier. When a black hole accretes matter at high rates, the energy relief by the accretion process can become so intense that it drives powerful outflows and heats surrounding gas, potentially limiting or even halting further accretion. This self-regulating feedback might prevent black holes from growing indefinitely, establishing a maximum mass related to the depth of their host galaxy's potential well and the efficiency of feedback coupling. Another constraint relates to the finite amount of matter available for black holes to accrete. Even in the most massive galaxies, the total stellar and gas mass, while enormous, is finite. A black hole cannot grow beyond some fraction of its host galaxy's total mass without fundamentally altering the galaxy's structure and dynamics. Observations suggest that typical supermassive black holes contain roughly 0.1% of their host galaxy's stellar mass, suggesting a natural ceiling imposed by galaxy formation processes. However, ultramassive black holes like the one in Holm 15A seem to push against these limits, containing larger fractions of their host galaxy's mass than typical systems. This might indicate that the formation conditions for these extreme objects differ from ordinary supermassive black holes, perhaps involving more efficient merger-driven growth or formation in particularly dense environments at early cosmic times. Some theoretical models predict that black holes might be able to grow to masses of hundreds of billions of solar masses under optimal conditions, particularly in the centers of the most massive galaxy clusters, where continued mergers could supply mass over extended periods. But whether such ultramassive black holes actually exist remains an open question. The practical observational challenge is that the most massive black holes, if they exist, would likely reside in the most distant, massive galaxies where our current measurement techniques struggle to provide precise mass estimates. Additionally, the finite age of the universe imposes a constraint. There has only been 13.8 billion years for black holes to grow from whatever seeds existed in the early universe. Even with sustained rapid accretion and multiple major mergers, there's only so much growth possible in the available time. Holm 15A and similar ultramassive black holes appear to represent systems that have achieved close to the maximum growth possible given cosmic age and astrophysical constraints. The comparison between Holm 15A's current quiescent state and the brilliant quasar phase that such massive black holes likely experienced earlier in cosmic history highlights the evolutionary nature of black hole activity. Quasars represent the most luminous, persistent sources of electromagnetic radiation in the universe, with some shining with the light of trillions of suns, all powered by supermassive black holes accreting gas at prodigious rates. The quasar phenomenon reached its peak in the universe's history, several billion years after the Big Bang, during an epoch when galaxy mergers were more frequent and galaxies contained larger reservoirs of cold gas available to fuel black hole accretion. Looking out to great distances and thus back in time, astronomers observed numerous brilliant quasars powered by black holes accreting gas and growing rapidly. Many of these distant quasars contain black holes with masses of billions of solar masses, already quite massive despite the universe's relative youth at those epochs. As we look at more nearby and thus more recent epochs of cosmic history, quasars become less common, replaced by a larger population of galaxies with relatively quiet central black holes, occasionally punctuated by lower-level activity or brief flares when material falls toward the black hole. Holm 15A represents the mature, quiescent phase of this evolutionary sequence. Today, the galaxy appears relatively inactive, without the signatures of vigorous accretion that would produce quasar-like luminosity. This doesn't mean the black hole is completely dormant. There might be low-level accretion occurring that our observations haven't detected, and the black hole remains capable of consuming any gas or stars that approach it. But compared to its likely past as a brilliant active galactic nucleus during periods of rapid growth, Holm 15A now sits relatively quietly at the center of its galaxy. This transition from active to quiescent reflects several factors. The galaxy has consumed or expelled much of its cold gas reservoir through past episodes of star formation and black hole feedback. The merger rate in the local universe has declined as cosmic expansion stretches distances between galaxies and groups, making major mergers less frequent. The black hole has likely grown so massive that its feedback effects are particularly strong, efficiently preventing gas from cooling and accreting. The result is a massive relic black hole that grew to enormous size through vigorous activity in the past, but now exists in a relatively quiet state, occasionally flickering to life when circumstances bring fresh fuel within its reach.
This cycle of activity and quiescence appears to be a common feature of supermassive black hole evolution. Observations of both nearby and distant galaxies reveal populations at various stages, some in vigorous accretion phases, displaying active galactic nucleus activity, others in transition states with moderate activity, and still others apparently quiescent. Individual galaxies likely cycle through these states multiple times over cosmic history, with activity triggered by merger events, close encounters with other galaxies, or instabilities that drive gas inward, followed by quiescent periods after the available fuel is consumed or feedback processes halt accretion. The total amount of mass a black hole accretes over its lifetime is reflected not only in its current mass, but also in the integrated energy it has released, which can be probed through observations of supermassive black holes at different epochs. By studying ultramassive black holes like the one in Holm 15A in their current quiescent state, and comparing them to observations of rapidly accreting quasars at earlier cosmic times, astronomers can piece together a comprehensive picture of how these objects grow and evolve over billions of years. Looking toward the future evolution of Holm 15A and its central black hole, we must consider the context of cosmic evolution over timescales far longer than the current age of the universe. The universe continues expanding, with the expansion rate governed by the cosmological constant, or dark energy, that pervades space. This accelerating expansion means that over time, galaxy clusters become increasingly isolated from one another as the space between them grows. Within gravitationally bound structures like the Abell 85 cluster, the expansion doesn't directly affect the cluster's size. The mutual gravitational attraction of the cluster's mass holds it together against the expansion. However, the expansion does mean that galaxies and groups outside the cluster are receding from Abell 85 at ever-increasing velocities, making future mergers with external systems increasingly unlikely. Within the cluster itself, individual galaxies continue to orbit through the cluster's gravitational potential, occasionally experiencing close encounters or collisions. Holm 15A, at the cluster's center, continues to have opportunities to merge with infalling galaxies, each merger adding to its stellar mass and potentially its central black hole's mass if the infalling galaxy contains its own supermassive black hole. Over the next hundreds of billions of years, these processes will continue, though likely at a declining rate as the cluster relaxes toward a more dynamically evolved state.
On truly cosmic timescales extending trillions of years into the future, the universe will look profoundly different from today. Star formation throughout the universe will gradually cease as galaxies exhaust their gas reservoirs and the expansion of space prevents new gas from falling into galaxies. The stellar populations in galaxies like Holm 15A will age, with the most massive, luminous stars having long since died, and the galaxy's light increasingly dominated by old, low-mass red stars and stellar remnants like white dwarfs, neutron stars, and stellar-mass black holes. The galaxy itself will likely have merged with many or all of the other galaxies in the Abell 85 cluster, forming an even more massive single galaxy encompassing the matter from hundreds of progenitor galaxies. The central black hole will have grown through merger events with other supermassive black holes from these consumed galaxies, potentially reaching masses of hundreds of billions of solar masses or more, truly staggering even by the standards of today's ultramassive black holes. This future megagalaxy will be a relatively quiet, dark place, with little ongoing star formation or dynamic activity, simply an enormous collection of aging stars orbiting the gravitational center dominated by the ultramassive black hole. Looking even further forward on timescales of 10 to the power of 19 years or more, even the stars themselves will begin to disappear. Close gravitational encounters between stars, accumulated over these immense timescales, will gradually eject stars from the galaxy, with some escaping to intergalactic space, while others fall into the central black hole. The galaxy will slowly evaporate, losing mass as stars are ejected, while the central black hole continues to grow by consuming unlucky stars. Eventually, after timescales almost incomprehensibly longer than the current age of the universe, the galaxy will have largely disappeared, with most of its stars either ejected or consumed, leaving primarily the central black hole as the dominant remaining object. And then, on even longer timescales that strain our ability to comprehend, if the predictions of quantum mechanics hold true, the black hole itself will begin to evaporate through Hawking radiation. Stephen Hawking's seminal work in the 1970s showed that black holes are not completely black, but instead emit thermal radiation due to quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes radiate at lower temperatures. For an ultramassive black hole like Holm 15A's, the Hawking temperature is extraordinarily low, far below even the temperature of the cosmic microwave background radiation that currently pervades the universe. Only after the universe expands and cools far below the black hole's Hawking temperature will the black hole begin net mass loss through evaporation. The timescale for a black hole to completely evaporate through Hawking radiation scales as the cube of its mass, making the evaporation time for ultramassive black holes almost unimaginably long. For a 40 billion solar mass black hole, the evaporation time is approximately 10 to the power of 100 years, far, far longer than the current age of the universe, which is merely about 10 to the power of 10 years. During this immense period, the black hole radiates away its mass energy extraordinarily slowly, gradually shrinking over googols of years. As it loses mass, its Hawking temperature increases, causing the evaporation rate to accelerate. In its final moments, when it is shrunk to perhaps stellar mass and then smaller still, the evaporation proceeds rapidly, with the black hole finally disappearing in a brief flash of high-energy radiation, converting the last of its mass into photons and particles that disperse into the cold, dark, almost empty universe. At that point, the black hole's long history from its formation in the early universe through its growth over billions of years to ultramassive scale, and then its slow evaporation over incomprehensible timespans, will finally conclude. The matter and energy that compose the black hole will have been returned to the universe in the form of radiation, closing a chapter that spanned the entire history of a galaxy and far beyond. The technological and observational advances needed to study objects like Holm 15A in greater detail will shape the future of supermassive black hole research. Current observations, while impressive, push the limits of existing telescopes and techniques. Measuring the mass of a black hole in a galaxy 700 million light-years away requires large telescopes with advanced spectrographs capable of gathering sufficient light and achieving high enough spectral resolution to measure stellar velocities.
Future extremely large telescopes, with primary mirrors measuring 30 or even 40 meters in diameter, will dramatically improve our ability to study distant galaxies in detail. These future giants will gather far more light than current facilities, allowing astronomers to obtain high-quality spectra from fainter and distant galaxies, extending the population of supermassive black holes we can study with stellar kinematics. Additionally, improvements in adaptive optics technology, which corrects for the blurring effects of Earth's atmosphere, will enable sharper images that can resolve finer details in galaxy cores. Space-based observatories offer complementary capabilities by avoiding atmospheric interference entirely and accessing wavelengths of light that don't penetrate Earth's atmosphere. Future X-ray missions will probe the hot gas in galaxy clusters with unprecedented sensitivity, revealing details of how supermassive black holes interact with their host galaxies through feedback processes. Infrared telescopes, building on the capabilities demonstrated by the James Webb Space Telescope, will peer through cosmic dust to study galaxy centers at high resolution, and will look back to earlier cosmic epochs when ultramassive black holes were in their active growth phases. Perhaps most exciting is the possibility of directly imaging black hole event horizons and their immediate environments. The Event Horizon collaboration demonstrated this capability by producing the first image of a black hole's shadow, the dark silhouette created by the event horizon against the bright emission from surrounding material, for the supermassive black holes in M87 and the Milky Way center. Extending this technique to more distant and more massive black holes remains challenging, but might become possible with expanded arrays of radio telescopes and advanced data processing techniques.
Gravitational wave astronomy opens an entirely new window onto black hole physics, and will ultimately provide direct observations of supermassive black hole mergers. The LIGO and Virgo detectors that first detected gravitational waves from merging stellar mass black holes operate at frequencies too high to detect supermassive black hole mergers, which produce gravitational waves at much lower frequencies. Future space-based gravitational wave observatories, particularly the Laser Interferometer Space Antenna mission planned for launch in the 2030s, will observe gravitational waves at frequencies ideal for detecting mergers of supermassive black holes with masses from hundreds of thousands to hundreds of millions of solar masses. LISA won't directly observe ultramassive mergers in the billion to tens of billions solar mass range, as these produce even lower frequency gravitational waves. But it will observe the precursor stages of such mergers and provide unprecedented information about supermassive black hole populations across cosmic time. Even lower frequency gravitational waves from the most massive black hole mergers can be detected through pulsar timing arrays, networks of precisely monitored pulsars that serve as a galaxy-spanning gravitational wave detector. These observations will directly reveal the rates and properties of supermassive black hole mergers, testing our theoretical models of how ultramassive black holes like Holm 15A assemble their current masses. Theoretical advances will parallel observational progress, with increasingly sophisticated simulations of galaxy formation and black hole growth. Modern cosmological simulations can follow the evolution of structure from the early universe through billions of years of cosmic history, tracking how gas and dark matter clump together to form galaxies, how supermassive black holes form and grow through accretion and mergers, and how feedback from black holes and stars affects galaxy evolution. These simulations require enormous computational resources, running on supercomputers with thousands of processors working in parallel for weeks or months to simulate the formation of even a single massive galaxy or galaxy cluster. As computational power continues to increase and the physical models implemented in simulations become more sophisticated and realistic, theorists will be able to make increasingly precise predictions about ultramassive black hole formation. By comparing these predictions to observations of objects like Holm 15A, astronomers can test and refine our understanding of the physics governing these extreme objects. Key questions that future observations and simulations must address include: what were the properties of the seed black holes from which today's supermassive black holes grew? How efficiently did early black holes accrete matter? And were there periods of super-Eddington accretion that violated the standard limits? How many major merger events did galaxies like Holm 15A experience? And what were the masses of the merging black holes? What role did environmental factors like location in galaxy clusters play in enabling extreme black hole growth?
The connection between ultramassive black holes and the broader questions of cosmology and fundamental physics deepens our appreciation for objects like Holm 15A. These black holes formed in the earliest stages of structure formation in the universe, with their seed black holes possibly dating to within the first few 100 million years after the Big Bang. Observations of extremely distant quasars powered by billion solar mass black holes when the universe was less than 1 billion years old tell us that rapid black hole growth occurred very early in cosmic history, during the epoch when the first galaxies were forming and the universe was transitioning from a largely neutral state to the ionized state we observe today. Understanding how such massive black holes form so quickly constrains models of early galaxy formation and the nature of the first generation of stars. The seed black holes that eventually grew into today's ultramassive black holes might have formed from the collapse of the very first massive stars, or they might have formed through direct collapse of primordial gas clouds into massive black holes without an intermediate stellar phase, or perhaps through more exotic mechanisms involving dark matter or other unknown physics. The extreme gravitational fields around ultramassive black holes also serve as natural laboratories for testing general relativity and probing the nature of space-time under extreme conditions. While general relativity has passed every test thrown at it so far, from solar system observations to gravitational wave detections, the regime near ultramassive black hole event horizons represents physics at the edge of our current understanding. Observations of stellar orbits and gas dynamics near these black holes, and eventually direct images of event horizon regions will test whether general relativity accurately describes gravity in these extreme environments, or whether modifications or corrections are needed. The information paradox, which questions whether information that falls into a black hole is truly lost or somehow preserved and eventually returned when the black hole evaporates, remains one of the deepest puzzles at the intersection of quantum mechanics and gravity. While we're unlikely to observe Hawking radiation from ultramassive black holes like Holm 15A, given their extraordinarily low temperatures, the theoretical framework we developed to understand black hole thermodynamics and information must apply to all black holes, regardless of mass. Progress on these fundamental questions often comes from thinking about extreme cases like ultramassive black holes and working out the implications of our theories in these limiting regimes. The interdisciplinary nature of black hole research brings together insights from multiple fields of physics and astronomy. Understanding objects like Holm 15A requires expertise in observational astronomy to gather and analyze data from telescopes, theoretical astrophysics to model black hole formation and growth, general relativity to describe the extreme space-time geometry near the black hole, cosmology to understand the large-scale structure and history of the universe in which these objects formed, and even quantum mechanics and particle physics when considering questions about event horizon physics and Hawking radiation. This convergence of disciplines makes supermassive black hole research a particularly rich area where advances in one field can illuminate puzzles in others. The discovery and characterization of ultramassive black holes has already influenced our understanding of galaxy formation, providing crucial constraints on the role of black hole feedback in regulating star formation. Future observations will continue to provide data that theorists must explain, driving the development of more comprehensive models of how the universe evolves from the simple, nearly uniform state shortly after the Big Bang to the rich structure of galaxies, clusters, and supermassive black holes we observe today.
On a more philosophical level, contemplating an object like the ultramassive black hole in Holm 15A invites reflection on the vast scales of space and time that characterize our universe. The 40 billion solar masses concentrated in a region roughly 1,500 astronomical units across represents a density and gravitational intensity that has no parallel in everyday human experience. The event horizon, while enormous by astronomical standards, is still utterly minuscule compared to the 700 million light-year distance we must look across to observe this object, and utterly insignificant compared to the tens of billions of light-years extent of the observable universe. Yet this black hole, one object in one galaxy among hundreds of billions of galaxies in the observable universe, encapsulates fundamental questions about the nature of space, time, matter, and gravity. Its formation history spans most of the age of the universe, from seed black holes in the first galaxies through billions of years of growth to the ultramassive object we observe today. Its future evolution will continue over timescales vastly longer than the current age of the universe, eventually culminating in complete evaporation through Hawking radiation after a period so long that the numbers involved become essentially meaningless in human terms. The study of ultramassive black holes also connects to broader questions about the universe's fate. We know the universe is expanding and that the expansion is accelerating due to dark energy. Current observations suggest this acceleration will continue indefinitely, leading to a future where galaxies outside gravitationally bound groups and clusters recede beyond our cosmic horizon, disappearing from view as they are carried away by the expansion of space itself. In this far future universe, isolated galaxy clusters like Abell 85 will evolve in relative isolation, slowly relaxing toward equilibrium states. The galaxies within clusters will merge over time, and eventually supermassive black holes will dominate the mass budget of the remaining structures. On timescales of 10 to the power of 14 years, stellar populations will have largely disappeared, either expelled from galaxies or consumed by central black holes. After 10 to the power of 40 years or so, even stellar remnants like white dwarfs may decay through exotic processes if current theories are correct. By 10 to the power of 100 years, even ultramassive black holes will have evaporated, leaving a universe containing only a thin soup of photons and fundamental particles, cold and dark, and essentially empty. This ultimate fate, sometimes called the heat death of the universe, represents the logical conclusion of the second law of thermodynamics applied on cosmic scales, with the universe gradually moving toward maximum entropy. Yet within this narrative of cosmic decline and eventual heat death, objects like Holm 15A represent remarkable achievements of structure formation and gravitational organization. In a universe governed by the second law of thermodynamics, where entropy must always increase and disorder must eventually triumph, the formation of stars, galaxies, and supermassive black holes represents local victories for order and structure. These objects concentrate mass and energy, creating regions of decreased entropy in their immediate vicinities, though always at the cost of increasing entropy elsewhere to satisfy the second law. Black holes in particular represent fascinating thermodynamic objects, with their own entropy proportional to the area of their event horizon rather than their volume. A black hole is in some sense the most efficient entropy storage mechanism possible, concentrating enormous entropy in a compact region of spacetime. The growth of supermassive black holes over cosmic time represents an increase in the universe's total entropy, as matter that falls into the black hole has its entropy counted toward the black hole's horizon area. When these black holes eventually evaporate through Hawking radiation, they will have converted the ordered mass energy of stars and gas that fell into them over billions of years into the thermal radiation spread throughout an immensely larger volume of space, representing an enormous increase in entropy. The human endeavor to understand objects like Holm 15A reflects our species' deep drive to comprehend the universe we inhabit. For most of human history, our ancestors looked up at the night sky and could only wonder about the nature of the stars and the vast dark spaces between them. The development of physics and astronomy over the past several centuries has given us increasingly powerful tools to probe the cosmos, from Galileo's first telescopes revealing moons orbiting Jupiter to today's sophisticated instruments that can measure the masses of black holes hundreds of millions of light-years away. Each advance in our understanding raises new questions and reveals new mysteries. A century ago, we didn't know that galaxies existed beyond our own Milky Way. We thought the universe was static and eternal. The discoveries that the universe is expanding, that it had a beginning in the Big Bang, that it contains dark matter and dark energy of unknown composition, and that supermassive black holes lurk at the centers of galaxies have revolutionized our cosmic perspective within living memory. The discovery and characterization of ultramassive black holes like Holm 15A represents one more step in this ongoing journey of discovery. These discoveries also highlight how much we still don't understand. Dark matter, which dominates the mass budget of galaxies and clusters and provides the gravitational framework for structure formation, remains unidentified after decades of searches for its constituent particles. Dark energy, which drives the accelerating expansion of the universe, is even more mysterious. understood only through its gravitational effects and not through any direct detection or theoretical prediction from fundamental physics. The physics of gravity at quantum scales, necessary to understand what happens at black hole singularities and during the black hole evaporation process, remains unknown, despite many promising theoretical approaches. The formation mechanisms for the first black hole in the universe, the seeds that grew into today's supermassive black holes, remain uncertain and debated. Even the precise masses of ultramassive black holes involve uncertainties, with different measurement techniques sometimes giving different results. Each answered question spawns new mysteries, ensuring that generations of astronomers and physicists yet to come will have profound questions to investigate and remarkable objects to study. In reflecting on Holm 15A and what this ultramassive black hole teaches us, several themes emerge. First, the incredible diversity and extremity of cosmic objects continually surprises us. Just when we think we understand the typical scales and properties of a class of objects, we discover outliers that push the boundaries and force us to expand our theoretical frameworks. Second, the interconnectedness of cosmic structures means that understanding one type of object requires understanding its relationships to other phenomena. Holm 15A cannot be understood in isolation, but only in context of its host galaxy, the galaxy cluster, the dark matter halo, the merger history, and the broader cosmic environment. And third, the vast scales of time and space involved in cosmic evolution humble our human perspectives, while also inspiring awe at the universe's grandeur. The billions of years over which Holm 15A grew to its current mass, the 700 million light-years its light traveled to reach us, and the googols of years over which it will eventually evaporate, stretch our cognitive abilities to their limits.
Fourth, the remarkable fact that we can study such objects at all, measuring their masses and inferring their histories from photons that have traveled across intergalactic space, testifies to the power of the scientific method and human ingenuity. The chain of reasoning that connects a spectrum showing shifted absorption lines to an inference about a 40 billion solar mass black hole involves sophisticated physics, careful observations, and rigorous mathematical analysis. Every step in this chain must be carefully validated, with uncertainties quantified and systematic errors considered. The result is reliable knowledge about objects and conditions far beyond anything we can directly experience. Fifth, the continuing mysteries and open questions remind us that science is an ongoing process, not a completed edifice. Our current understanding of ultramassive black holes, while impressive, surely contains gaps and possibly errors that future observations will reveal. The questions we ask today may be refined or even replaced by different questions as our understanding deepens. Finally, objects like Holm 15A connect us to the deepest questions about existence itself. Why does the universe exist at all? Why do the laws of physics take the forms they do? Are the values of fundamental constants like the gravitational constant and the speed of light arbitrary or determined by some deeper principle? Could different universes with different physical laws exist? And if so, what selects the particular universe we inhabit? While studying supermassive black holes doesn't directly answer these metaphysical questions, it does inform them by revealing what our particular universe is capable of producing under the laws of physics that govern it. The fact that gravity can concentrate 40 billion solar masses into a region a few 100 billion kilometers across, creating a space-time geometry so warped that not even light can escape, represents one of the universe's most extreme possibilities. That such objects not only exist but play crucial roles in galaxy formation and evolution tells us something profound about the nature of our cosmos. As we continue to observe and study Holm 15A and other ultramassive black holes, we can anticipate many discoveries ahead. More precise mass measurements will refine our understanding of the black hole mass spectrum and potentially reveal whether there truly is an upper limit to black hole mass. Detailed observations of stellar kinematics and gas dynamics in brightest cluster galaxies will clarify the relationship between ultramassive black holes and their host galaxies, testing whether they follow the same scaling relations as less extreme systems or whether different physics applies. Gravitational wave detections will eventually provide direct observations of supermassive black hole mergers, revealing the dynamics of these collisions and testing general relativity in the strong field regime. Studies of high redshift quasars will trace the early growth of supermassive black holes and constrain models of seed black hole formation. Advanced simulations will model the full history of ultramassive black hole formation in cosmological context, making predictions that observations can test. Each of these lines of investigation will contribute pieces to the puzzle, gradually building a more complete picture of how these remarkable objects form, grow, and influence their cosmic environments. The ultramassive black hole in Holm 15A stands as a monument to the universe's ability to create structures of almost unimaginable extremity. From our vantage point 700 million light-years away, we observe this object not as it exists today, but as it was when light left it 700 million years ago, when Earth was in the Neoproterozoic era and life was just beginning to diversify into the complex forms that would eventually fill the world's oceans and land. The light we detect today began its journey from the extreme gravitational environment around a black hole containing the mass of 40 billion suns, traveled across intergalactic space, through expanding universe, and finally entered our telescopes to be analyzed by astronomers seeking to understand one of the cosmos's most extreme objects. In that light is encoded information about stellar velocities, gravitational fields, and the history of galaxy formation stretching back billions of years. By carefully analyzing that information with our most sophisticated instruments and theories, we can peer into the heart of a distant galaxy and characterize an object that represents the ultimate endpoint of gravitational collapse, a region where space-time itself is warped beyond our everyday intuition and where the universe's most fundamental laws play out in their most extreme form. This is the power and the promise of astronomy, that by studying light from distant sources, we can understand the universe's most exotic objects and, in doing so, better understand the cosmos we inhabit and our place within it. You're right. Let me continue to reach the full 20,000 words as requested. The formation of seed black holes in the early universe remains one of the most compelling puzzles in modern astrophysics, and understanding this process is crucial to explaining how ultramassive black holes, like the one in Holm 15A, could grow to their current sizes. The standard scenario for seed black hole formation involves population 3 stars, the first generation of stars that formed in the universe when the only elements available were hydrogen, helium, and trace amounts of lithium produced in the Big Bang nucleosynthesis. These primordial stars, forming from chemically pristine gas clouds that had never been enriched by previous stellar generations, could grow to enormous masses, potentially hundreds of times the mass of the Sun. Without heavier elements to facilitate cooling of gas clouds, the collapse of primordial gas would naturally produce very massive stars. When these population 3 stars exhausted their nuclear fuel and collapsed, they would form black holes with masses potentially ranging from tens to hundreds of solar masses, providing the seeds from which supermassive black holes would grow. However, detailed calculations of black hole growth through accretion reveal significant challenges in growing these relatively modest seed black holes to the billion solar mass behemoths observed in quasars when the universe was less than 1 billion years old. Even if a seed black hole accreted matter at the maximum Eddington rate continuously, the exponential growth timescale is approximately 50 million years to increase its mass by a factor of e, the base of natural logarithms. To grow from 100 solar mass seed black hole to 1 billion solar mass black hole would require roughly 20 such e-folding times, or about 1 billion years of sustained Eddington-limited accretion. This barely fits within the available time to produce the massive quasars observed at high redshift, and it requires extremely optimistic assumptions about continuous, uninterrupted accretion at the maximum possible rate. In reality, accretion is likely episodic, with periods of rapid growth interspersed with quiescent phases when fuel is unavailable. Additionally, feedback from the accreting black hole itself likely disrupts and heats surrounding gas, reducing accretion efficiency. These considerations have led some theorists to propose alternative scenarios for forming more massive seed black holes that could grow more quickly to supermassive scales.
One alternative scenario involves the direct collapse of primordial gas clouds into massive black holes without an intermediate stellar phase. Under specific conditions in the early universe, where certain cooling processes are suppressed, gas clouds of masses of tens of thousands to hundreds of thousands of solar masses might collapse directly into black holes. These direct collapse black holes would provide much more massive seeds, with masses perhaps 10,000 to 100,000 times that of the Sun, giving them a substantial head start in the race to grow to supermassive scales. The conditions required for direct collapse are quite specific, involving gas that has been enriched with molecular hydrogen, but then has that molecular hydrogen destroyed by ultraviolet radiation from nearby early galaxies, preventing the gas from cooling efficiently and fragmenting into individual stars. Whether such conditions were common enough in the early universe to produce a significant population of direct collapse black holes remains uncertain, and depends on details of early galaxy formation and the radiation environment in the first billion years after the Big Bang. Observations of the most distant quasars provide crucial constraints on seed black hole formation mechanisms, as they reveal the masses of black holes that existed at specific early times, constraining how much growth was needed and therefore what seed masses and accretion histories were required.
Another exotic possibility for seed black hole formation involves primordial black holes, hypothetical objects that might have formed in the very early universe, perhaps in the first seconds after the Big Bang, from density fluctuations in the primordial plasma. If sufficiently massive primordial black holes exist, they could have served as seeds for supermassive black hole growth. However, constraints from various observations, including studies of the cosmic microwave background, gravitational lensing, and the present-day abundance of black holes, severely limit the possible abundance and mass range of primordial black holes. Most scenarios for abundant primordial black holes have been ruled out, though certain narrow windows remain viable. An even more speculative possibility involves black holes formed from dark matter, either through direct collapse of dark matter halos or through exotic physics involving dark matter particles. These scenarios remain highly theoretical and lack direct observational support, but they illustrate the range of possibilities theorists have considered in attempting to explain the rapid early growth of supermassive black holes. The role of environment in determining black hole growth rates and ultimate masses deserves deeper consideration. Holm 15A resides in the Abell 85 galaxy cluster, specifically at the cluster center and the deepest part of the gravitational potential well. This location provides significant advantages for black hole growth over cosmic time. Galaxy clusters form at the intersections of cosmic filaments, the large-scale structures along which matter flows in the cosmic web. Material flowing along filaments toward the cluster brings gas in galaxies that can fuel black hole growth. The cluster center, being the location of strongest gravitational attraction, preferentially captures infalling material. Brightest cluster galaxies at cluster centers grow primarily through mergers with other cluster galaxies and by accreting smaller galaxies that fall toward the center. Each such merger brings an opportunity for the central black hole to grow, both through direct merger with the companion galaxy's black hole and through merger-triggered gas accretion. Over billions of years, a central cluster galaxy might experience dozens of mergers, each contributing to black hole growth. Environmental density also affects gas accretion rates. In the central regions of galaxy clusters, the density of hot intercluster gas can be substantial, providing a reservoir of material that can potentially cool and accrete onto the central black hole. While most of this gas is heated to millions of degrees by gravitational compression as it falls into the potential well, making it difficult for the gas to cool and accrete efficiently, cooling flows can develop under certain conditions where the densest gas at the cluster core radiates away its thermal energy and flows inward. The central black hole's activity can regulate this process through feedback, where energy injected by jets or radiation from the accreting black hole heats the surrounding gas and prevents runaway cooling. This self-regulating cycle means that central cluster black holes likely maintain lower accretion rates than their isolated counterparts during quiescent periods. But the sheer duration of time they spend in these gas-rich environments means significant mass can accumulate. Additionally, the tidal disruption of stars passing close to the black hole provides another accretion channel that depends on the stellar density in the galactic core, which is enhanced by the multiple merger events that central cluster galaxies experience. The relationship between dark matter halo mass and black hole mass at the extreme end of the mass function provides another avenue for understanding ultramassive black holes. Theoretical models of galaxy formation typically predict relationships between dark matter halo properties and the properties of galaxies and black holes that form within those halos. The most massive dark matter halos in the universe, with masses of 10 to the 15 solar masses or more, correspond to galaxy clusters like Abell 85. The central galaxies in these massive halos, having assembled through numerous mergers over cosmic time, host the most massive black holes. Simulations of galaxy cluster formation show that the merger trees leading to the most massive halos at the present day are particularly complex, with many major merger events and a sustained high rate of minor mergers. Translating these halo merger histories into predictions for black hole growth requires modeling the physics of how black holes grow during galaxy mergers, how much gas is available for accretion at different epochs, and how feedback processes regulate growth. State-of-the-art cosmological simulations that include sophisticated models of black hole growth and feedback can now make reasonably reliable predictions for the black hole mass function at different cosmic epochs. Comparing these predictions to observations of ultramassive black holes like Holm 15A provides crucial tests of our theoretical frameworks. If observations reveal more ultramassive black holes than predicted, it might indicate that our models underestimate black hole growth efficiency, or that we're missing important growth mechanisms. Conversely, if ultramassive black holes are rarer than predicted, it might suggest that feedback processes are more effective at limiting black hole growth than current models assume, or that there are astrophysical bottlenecks that prevent black holes from reaching the largest possible masses. Current evidence suggests that ultramassive black holes are quite rare, with only a handful of confirmed or candidate objects with masses above about 20 billion solar masses. This rarity is actually consistent with theoretical expectations, as such objects should only form in the most massive dark matter halos at the centers of major galaxy clusters, which are themselves quite rare. The steep decline in the black hole mass function at the highest masses reflects both the rarity of environments capable of producing such objects and the increasing difficulty of continuing to grow as black holes become more massive and their feedback effects become more powerful. The impact of ultramassive black holes on their host galaxies and surrounding environments extends far beyond the immediate vicinity of the black hole itself. When active, supermassive black holes launch jets of relativistic particles and magnetic fields that can extend for millions of light years into intergalactic space. These jets, powered by the rotational energy of the black hole and the magnetic fields threading the accretion disk, transport enormous amounts of energy from the galactic center into the surrounding intercluster medium. The jets inflate giant bubbles or cavities in the hot gas, displacing and heating the gas over vast volumes. These bubbles are readily observable in X-ray images of galaxy clusters as regions of reduced X-ray emission, indicating where the hot gas has been pushed aside by the jet-driven outflows. The mechanical energy deposited by these jets can equal or exceed the radiative energy output of the active black hole, making jets a crucial component of black hole feedback. For a black hole as massive as the one in Holm 15A, even relatively modest accretion rates can power substantial jet activity. The black hole need not be accreting at anywhere near the Eddington limit to produce jets with tremendous mechanical power. In fact, many of the most powerful radio sources indicating strong jet activity are associated with black holes that appear to be accreting at relatively low rates compared to bright quasars. This regime, sometimes called radiatively inefficient accretion, occurs when the accretion rate is low enough that the infalling matter cannot efficiently radiate away its energy before crossing the event horizon. The resulting accretion flow is geometrically thick and hot, with much of the energy going into the kinetic energy of outflows rather than radiation.
These radiatively inefficient flows are particularly efficient at producing jets, making them potentially quite important for the feedback effects of massive black holes in present-day galaxy clusters. Evidence for past jet activity in Holm 15A might be found in radio observations revealing extended emission or X-ray observations showing cavities in the surrounding gas, though the current activity level appears to be quite low.
The study of stellar dynamics in the cores of massive elliptical galaxies has revealed a rich phenomenology beyond simple stellar orbits. Stars in galactic nuclei can exist in a variety of orbital configurations, from nearly circular orbits in a preferred plane to highly eccentric orbits with large inclinations. The distribution of orbital shapes and orientations, sometimes called the orbital anisotropy, affects the relationship between observed stellar velocities and the underlying gravitational potential. When astronomers model stellar kinematics to infer black hole masses, they must make assumptions about this orbital distribution or attempt to constrain it from the data itself. Different assumptions can lead to different inferred black hole masses, contributing to measurement uncertainties. In galaxies that have experienced multiple major mergers, like Holm 15A, the orbital structure can be quite complex, reflecting the mixing of stellar populations from multiple progenitor galaxies with different orbital characteristics. The large stellar core observed in Holm 15A adds another layer of complexity, as the depletion of stars in the central region affects the gravitational potential and the interpretation of velocity measurements. Recent advances in stellar dynamics modeling have employed sophisticated techniques that can simultaneously fit both the spatial distribution of stars and their velocity distribution as a function of position in the galaxy, using self-consistent models that satisfy the fundamental equations governing stellar systems in equilibrium. These Schwarzschild modeling techniques, named after astronomer Martin Schwarzschild, who pioneered this approach, construct a library of possible stellar orbits in a specified gravitational potential, and then determine which combination of orbits best reproduces the observed surface brightness and kinematic data. By varying the assumed black hole mass and dark matter distribution, and finding which combination yields the best fit to observations, astronomers can determine the black hole mass and characterize its uncertainties. For Holm 15A, such modeling indicates a black hole mass around 40 billion solar masses, though the exact value depends on assumptions about the dark matter distribution and the orbital structure, with quoted uncertainties typically ranging from about 20 to 60 billion solar masses. This substantial uncertainty range reflects the genuine challenges in measuring black hole masses at such large distances, where even the best data have limited spatial resolution and signal-to-noise ratios. The phenomenon of wandering black holes, supermassive black holes that have been displaced from their galaxy centers by gravitational wave recoil or other dynamical processes, represents an important consideration in understanding galaxies with complex merger histories. When two supermassive black holes merge, if the gravitational wave emission is sufficiently asymmetric, the resulting recoil can impart velocities of hundreds or even thousands of kilometers per second to the merged black hole. For most galaxy potential wells, escape velocities range from several hundred to over 1,000 kilometers per second, meaning that moderate to large recoil kicks could eject black holes from their host galaxies or at least displace them significantly from the galactic center. A displaced black hole would oscillate through the galaxy, passing back and forth through the center with an oscillation period determined by the galaxy's mass distribution. Dynamical friction gradually damps these oscillations over timescales of tens to hundreds of millions of years, eventually returning the black hole to the center. During the oscillation phase, the black hole sweeps through a large volume of the galaxy, interacting with stars and gas throughout that volume. For Holm 15A, the large stellar core could potentially reflect past episodes of black hole wandering following one or more major merger events. A black hole oscillating through the galaxy core would interact with stars throughout the oscillation volume, potentially contributing to excavating the observed stellar deficit. However, the core size in Holm 15A is large enough that binary black hole interactions before the final merger likely play a more important role. The binary phase, when two supermassive black holes orbit each other with separations of light years to tens of light years, efficiently ejects stars through three-body gravitational interactions. The timescale for this core excavation depends on the black hole binary's mass, separation, and orbital parameters, as well as the stellar density in the environment. For massive binaries with total masses of tens of billions of solar masses, the ejection rate can be substantial, removing billions of solar masses worth of stars from the core region over the tens to hundreds of millions of years the binary takes to coalesce. Multiple merger events over Holm 15A's history would have multiple binary phases, each contributing to core excavation and potentially creating the unusually large stellar deficit observed today. The observational signatures of past black hole activity in galaxies like Holm 15A can persist for millions to hundreds of millions of years after the activity has ceased. Radio emission from relativistic jets can continue radiating for tens of millions of years as the jet plasma expands and ages, gradually losing energy through radiation and adiabatic expansion. X-ray cavities blown in the hot intracluster gas can remain visible for hundreds of millions of years, as they rise buoyantly through the cluster atmosphere. Even the large-scale distribution of gas and metals in the cluster can retain memory of past energetic events for substantial periods. Astronomers can use these fossil signatures to reconstruct the activity history of central black holes, even when those black holes are currently quiescent. For Holm 15A, detailed multi-wavelength observations searching for such signatures could reveal the timing and energetics of past activity episodes, constraining how recently the black hole was in an active accretion phase and how much energy it has injected into its surroundings over time. Combining such observational constraints with theoretical models of black hole growth and feedback provides a more complete picture of the black hole's life history. The chemical evolution of galaxies provides another window into understanding black hole growth and its effects. When massive stars explode as supernova, they synthesize and disperse heavy elements into the interstellar medium, gradually enriching subsequent generations of stars with elements heavier than hydrogen and helium. The metallicity of a stellar population, its abundance of heavy elements, thus serves as a clock indicating when those stars formed, with older populations generally being more metal-poor and younger populations more metal-rich. The metallicity distribution of stars in a galaxy's central regions, therefore, can provide information about the star formation history and, indirectly, about how the central black hole grew. Periods of vigorous black hole accretion often coincide with periods of intense star formation, both triggered by gas-rich galaxy mergers that funnel gas toward the galaxy center. The resulting stellar populations formed during these episodes should show specific metallicity patterns reflecting the composition of gas available at that time. For massive elliptical galaxies like Holm 15A, stellar populations are generally old and metal-rich, having formed most of their stars billions of years ago during the galaxy's early assembly. The cessation of star formation in these systems, often called quenching, is thought to be closely related to black hole feedback preventing gas from cooling and forming new stars. The metallicity patterns in the galaxy's stars therefore encode information about when this quenching occurred and how star formation proceeded before quenching. Detailed spectroscopic studies that can separate the light from different stellar populations with different ages and metallicities, sometimes called stellar population synthesis or stellar archaeology, allow astronomers to reconstruct the star formation history in considerable detail. For Holm 15A, such studies could reveal whether the galaxy experienced extended star formation over billions of years, or whether star formation occurred in distinct episodes separated by quiescent periods, each pattern having different implications for the black hole's growth history and its impact on the galaxy. The distribution of heavy elements in the intracluster medium provides complementary information about the history of stellar and black hole activity. Supernovae and stellar winds disperse metals from galaxies into the surrounding gas, where they can be detected through X-ray spectroscopy of emission lines from highly ionized elements like iron, silicon, and oxygen. The metallicity of intracluster gas in clusters like Abell 85 typically reaches about 1/3 of solar values, indicating substantial enrichment from stellar nucleosynthesis over cosmic time. The spatial distribution of metals in the cluster gas can reveal how they were dispersed, with higher metallicities near galaxies indicating recent or ongoing metal injection, while more uniform distributions suggest efficient mixing over long timescales. Outflows from active galactic nuclei can transport metals from galactic centers into the surrounding intracluster medium, distributing the products of stellar nucleosynthesis over large volumes.
The metallicity patterns in Abell V85 could therefore provide evidence for past activity from Holm 15A's central black hole, particularly if metal-enriched regions correlate with structures like X-ray cavities that indicate jet propagation. The multi-messenger astronomy revolution, which combines observations of electromagnetic radiation with gravitational waves, neutrinos, and cosmic rays, promises to provide unprecedented insights into black hole physics. While current gravitational wave detectors like LIGO and Virgo are sensitive primarily to stellar mass black hole mergers, future detectors will extend our reach to supermassive black holes. The Laser Interferometer Space Antenna, planned for launch in the mid-2030s, will observe gravitational waves in the millihertz frequency range, ideal for detecting mergers of supermassive black holes with masses from tens of thousands to tens of millions of solar masses. Such observations would provide direct measurements of black hole masses and spins with exquisite precision, test general relativity in the strong field regime, and reveal the population of black hole binaries at various stages of their evolution. For ultramassive black holes in the billions to tens of billions of solar mass range, gravitational waves peak at even lower frequencies accessible only through pulsar timing arrays. These experiments use networks of precisely timed millisecond pulsars scattered across the galaxy as a galaxy-sized gravitational wave detector, sensitive to nanohertz frequency gravitational waves. Recent results from pulsar timing array collaborations have reported evidence for a gravitational wave background at nanohertz frequencies, consistent with the cumulative signal from many supermassive black hole binaries throughout the universe. While this background doesn't yet allow detection of individual mergers, it provides strong evidence that supermassive black hole mergers occur at substantial rates and that they produce gravitational waves with the expected properties. As pulsar timing arrays accumulate more data and achieve better timing precision, they may eventually detect individual loud mergers involving the most massive black hole binaries. A merger involving a black hole as massive as the one in Holm 15A, if it were to occur within a few hundred million light-years, might be detectable as an individually resolvable event. Such detections would revolutionize our understanding of ultramassive black hole mergers, providing direct measurements of the black hole masses and spins involved, the merger dynamics, and any recall velocity imparted to the remnant. Combining gravitational wave observations with electromagnetic observations of the same systems would allow unprecedented insights into the environment surrounding merging black holes and the effects of mergers on their host galaxies. The theoretical framework describing black holes, general relativity, predicts specific observable signatures that can be tested through increasingly precise observations. One of the most fundamental predictions is the no-hair theorem, which states that black holes are characterized completely by just three parameters: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole or fell into it is lost, erased by the black hole's formation and subsequent evolution. This remarkable simplicity means that once we measure a black hole's mass and spin, we have completely characterized the object's classical properties. Testing the no-hair theorem requires observations precise enough to determine both the black hole's mass and its spin independently, then verifying that other observed properties are consistent with general relativity's predictions for an object with those parameters. For supermassive black holes and active galactic nuclei, where we can observe the accretion disk and jet close to the black hole, various techniques can constrain the black hole spin. For quiescent black holes like Holm 15A's, direct spin measurements are extremely challenging, although in principle, future observations with sufficient resolution might constrain spin through its effects on stellar orbits or gas dynamics very close to the black hole. The spin of supermassive black holes carries important information about their growth histories. Black holes grown primarily through gas accretion should have high spins approaching the maximum allowed values, as accreting gas adds angular momentum aligned with the black hole's rotation, spinning it up over time. Conversely, black holes grown primarily through mergers might have lower spins if the mergers involve black holes with randomly oriented spins that partially cancel when the holes merge. For ultramassive black holes like Holm 15A's, which almost certainly grew substantially through major mergers, we might expect moderate spins reflecting the stochastic nature of merger-driven growth. However, if the mergers tended to be aligned, perhaps because of preferred orientations of infalling galaxies related to the large-scale structure, the spin could be higher.
gas accretion between mergers would also contribute to spin-up. The actual spin of Holm 15A's black hole, if it could be measured, would provide a valuable constraint on which growth mechanisms dominated and how aligned or random the accretion and merger events were over cosmic time. The phenomenon of frame dragging, where a rotating black hole drags space-time around it with it, creates a region called the ergosphere outside the Hutton horizon, where nothing can remain stationary relative to distant observers. In the ergosphere, space-time itself is rotating, dragging everything along with the black hole's rotation. For a maximally spinning black hole, the ergosphere extends quite far from the horizon, reaching out to twice the Schwarzschild radius at the equator. Objects in the ergosphere can still escape to infinity, unlike objects inside the event horizon, but they cannot remain stationary and must orbit in the same direction as the black hole's rotation. The ergosphere is also the region where energy extraction from rotating black holes becomes possible through processes like the Penrose process or the Blanford's-Nayak mechanism, which can extract rotational energy and convert it into electromagnetic energy, powering jets. If Holm 15A's black hole rotates rapidly, it possesses tremendous rotational energy that could potentially power jets if the right magnetic field configuration exists. The rotational energy of a maximally spinning 40 billion solar mass black hole equals approximately 10 to the 61 joules, an almost incomprehensible amount of energy equivalent to about 100 million solar masses worth of rest mass energy. Tapping even a small fraction of this energy could power tremendous energetic outflows.
The information paradox, one of the deepest puzzles in theoretical physics, takes on interesting characteristics when considered for ultramassive black holes. The paradox arises from the apparent conflict between quantum mechanics, which requires that information is never truly lost, and black hole thermodynamics, which suggests that information falling into a black hole cannot be retrieved. Hawking's original calculation of black hole evaporation indicated that black holes radiate thermally, meaning the outgoing radiation carries no information about what fell in, only depending on the black hole's mass, charge, and spin. If black holes evaporate completely through this thermal process, information appears to be destroyed, violating a fundamental principle of quantum mechanics. Various resolutions to this paradox have been proposed, including the possibility that information is encoded in subtle correlations in the Hawking radiation, that it's stored in a remnant left after evaporation, or that it's somehow transferred to another universe or region of spacetime. Recent theoretical work using tools from quantum information theory and holography has suggested that information might indeed be preserved in Hawking radiation through complex quantum entanglement between the outgoing radiation and the black hole's internal state. For ultramassive black holes, the information paradox takes on extreme characteristics due to the enormous entropy such objects possess. The entropy of a black hole scales as the area of its event horizon, which for Holm's 15A's black hole amounts to approximately 10 to the 91 bits of information. This staggering amount of entropy means that an inconceivably vast amount of information could be stored in the black hole's quantum state. If this information is eventually returned through Hawking radiation over the black hole's evaporation timescale of 10 to the 100 years, the rate of information return would be extraordinarily slow, with each bit taking about 10 to the 9 years on average to emerge. The quantum state describing such a black hole, if we could somehow write it down, would require more information than is contained in all the particles in the visible universe. These considerations highlight the profound challenges facing any complete quantum theory of gravity, which must explain how such vast amounts of information are stored, processed, and eventually retrieved through the Hawking evaporation process. In conclusion, the ultramassive black hole at the center of Holm's 15A represents far more than simply an extreme object defined by its 40 billion solar mass weight. It stands as a cosmic monument to billions of years of structure formation, countless galaxy mergers, and the fundamental processes that govern how matter and energy interact under gravity's inexorable pull. From its origins as a seed black hole in the early universe, through its growth during vigorous quasar phases and dramatic merger events, to its current quiescent state and its eventual fate of evaporation in the unimaginably distant future, this black hole story spans the entire history of the cosmos and beyond. Every aspect of its existence connects to profound questions in physics and astronomy: the nature of gravity in extreme environments, the role of black holes in galaxy evolution, the formation of structure in the expanding universe, and the ultimate fate of matter and information. Through continued observations with ever more powerful instruments and continued theoretical work developing and testing our models, we will undoubtedly learn much more about Holm's 15A and similar objects in the years and decades ahead. Each discovery adding to our understanding of the universe's most extreme phenomena and pushing the boundaries of human knowledge ever outward into the cosmic unknown.
This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.